Good day, my name is Emmanuel Villanueva, and I am here to present my thesis topic, Determination of Pupillary Distance using YOLO algorithm for the 37th EC colloquium happening third quarter of the school year 2019-2020. Allow me to start with the introduction. So, pupillary distance is the distance between the two pupils of a person. This can greatly vary depending on race, gender, physical features, and other genetic variables. So basically, it is the distance between two pupils from left to right. This is going to be crossing the bridge of the nose, and the measurement of pupillary distance is currently done with a ruler or a pupillary distance ruler. The statement of the problem is that the estimation procedures using a ruler can affect with personal bias with the measurement of pupillary distance by the optometrist. So since the measurement is being done manually with a ruler, due to the nature of millimeter being a very small scale, it is easy to incorrectly read the actual distance of the pupillary distance. This can be affected by personal bias or human error such as physical movement of the subject or the ruler itself. So it's very easy to have the reading be incorrectly be reported or given depending on the nature or rather or the setting of how the pupillary distance is taken. So this is the conventional method of measuring pupillary distance. So right now we're using rulers to measure the distance between two pupils. So as you can see, it's very easy to miscalculate or misread these scales, especially if it's in millimeters. That's the problem that we're trying to solve. So the objectives of this study is to automate the determination of a subject's pupillary distance through the use of image processing while taking into account or consideration the specific objectives, such as to develop a prototype that will measure pupillary distance. Number 2, to apply image processing on captured images. Number 3, use YOLO algorithm or the You Only Look Once algorithm in capturing the pupil of the subject. And number 4, to test the accuracy of results by comparing manual and automated measurement results. So moving forward with the scope and the limitations, the scope of the research focuses on the determination of the distance between the pupils. So for the scope, we would completely focus on the determination of the pupillary distance, while the delimitations of the study is that no external interference such as glasses or hair should be present while capturing the subject's eyes. This is in order to avoid any misreading or incorrect measurements during the process of data gathering, and that the eye should not suffer from any form of ailments such as anisocoria, ptosis, and coloboma, since this may affect the reading of pupillary distance, since we measure the iris to get the measurement of the pupils of the subject. So having any sort of pupillary ailments would make it difficult for us to determine the actual measurement of pupillary distance. So the significance of the study affects 3 key people. So automating the detection of PD would be beneficial for the researcher, since this would open up the researcher's knowledge regarding optometries or optometry in the field of eyes and medicine, while it would also be beneficial for optometrists since the development of the prototype could speed up the process of determining pupillary distance and by automating the whole procedure while also allowing them to produce accurate results. And lastly, for future researchers, as this study can be used as a resource for citation and improvement with future studies relating in the field of pupillary distance or optometry. So the methodology follows the waterfall methodology steps, as we would be following different phases one at a time in order to move towards the next phase. So we have 6 different phases here, namely its planning, analysis, design, coding, calibration, and data gathering. So for the planning part, this involves the determination of what is the problem at hand and if it is possible to be solved. So this involves the application or rather the study and even the collection of related articles or literature to the topic involved, while finding gaps and assessing how to fill the said gaps in the study. So how do we improve existing studies regarding this particular field? Once that is done, we move forward with the analysis stage. So the analysis is the determination of a solution to the problem that was found in the planning phase. This involves as to how the problem found in the planning phase be solved through the use or rather through the application of engineering principles. The third step is that once analysis is done, we would have to study, or rather determine different components, determine the design, determine the significance of every single component and how they would be connected with one another in order to become the actual solution to the problem that was found. So this involves the creation of the model itself, of the actual prototype, and planning as to what will be the different components going to be used and how they are going to be used. So this involves explanation of the block diagram, which we would get to later on as well. Moving forward, for the fourth step, this is the coding part. So the coding is the creation of the software that is necessary for the prototype to function as expected. So as Face's name itself, which is coding, this involves coding or telling how the components should behave, while the main coding language used for the development of the prototype, or rather for the software of the prototype, is Python. While for image processing, OpenCV was used and TensorFlow was applied for the application of YOLO algorithm. Combining all those elements, it proves to be a solution to the problem that was found in the planning stage with the application, or rather through analysis and taking into consideration the objectives that are listed down in the analysis phase as a solution to the problem. So calibration, the fifth step. In order to make detection more accurate or much more faster, the developed device or prototype was subjected to calibration, wherein data set was fed into the model so that the system would detect eyes with better accuracy. And lastly, once the prototype has been created, we proceed with data gathering. This was done completely with respect to the manual measurement, as we would be comparing the results with them later on as a gauge to see how accurate the developed prototype is. So a total of 30 subjects with 5 attempts each was used for the data gathering procedure. Moving forward, we could see that the conceptual framework is a straight process wherein the input would be the image taken from the camera. The process is the application of YOLO algorithm in the detection of the eyes and image processing on captured images. And lastly, the output would be pupillary distance in terms of millimeter. As for the block diagram, we could see 5 different components in the developed system. One, which is the power source, which powers the whole prototype. SD card, which holds the operating system for the prototype and also the images that are going to be used. Camera, which is the main input of the device. This is responsible for determining the pupils, or rather the eyes of the subject. All of those will be processed inside the Raspberry Pi, where the developed program has been uploaded. And lastly, the results would be displayed on the LCD screen. So the image processing result, as you can see, would have 4 different figures. Figure 4A shows that the raw image of the subject. So initially, once an image has been captured, this is what it would look like. After processing, or rather capturing the raw image, it would be converted into grayscale in order to give way for figure 4C, because we will be applying Sobel filter on the image, and Sobel filter is only applied on grayscale images, so it's imperative that the image should be converted into grayscale first. So once Sobel filter is applied, noise reduction is to be applied as well in order to remove the contour of the faces and leave us with a very clear circle which represents the iris of the subject. We would then apply modified circle algorithm in order to determine the center or radius of the pupil, and from there we would be able to compute the distance between 2 pupillary distances. So the YOLO algorithm application, as you can see, the green line denotes the distance between the 2 pupils, while the green dots in the center of the eyes is the actual pupil of the subject. So you could see there would be 2 pupils in this particular image, and the line between them would be the distance. The developed prototype looks simply like this. This is the front side of the prototype. The LCD touchscreen in front can accept inputs in terms of touch, while the back side of the prototype is where the user, or rather the subject, could align their eyes directly into the prototype's camera to have their eyes scanned. So this is the GUI of the developed prototype. As you can see, there would be a reading of length in terms of millimeter in the left side pane, while the image of the subject would be projected onto the right side with the reading of pupils and the distance itself. And the results and discussions, as we've mentioned before, 30 subjects has been used, each one with 5 attempts in order to account for the gaze, focus, light on the subject's face and eyes, and after 5 different attempts, it would be averaged. Once averaged, the computed value, or rather the average value, would then be compared with the manually measured or the conventional method of determining pupillary distance. As you could see, we would have a very small difference when it comes to the difference, or rather the measurement of manually measured pupillary distance and the computed pupillary distance. Also, it is worth noting that this is in terms of millimeters. So what we're seeing, for example, in subject 1 is that the manually measured pupillary distance would be 61 millimeters, while for the computed average of the subject's pupillary distance would be 61.646. So we only have a difference of 0.646 millimeters between the two readings. For the scatter plot of the study, or rather the data, we could see that there is huge correlation between the data, since the data that was developed, or rather gathered, was subjected to regression analysis. As we could see, there is a regression value of 0.99149. The data itself shows that there is a very close correlation between the projected data, or the actual values, using the ruler in order to measure the pupillary distance of the subject, while the blue dots in the graph denotes the subject, or rather the results from the automated, or rather computed pupillary distance of the subject. So we could see that the values are very close. So for null hypothesis, wherein there exists a strong correlation between the values being compared, if we could see that the R value is nearing towards +1, while alternative hypothesis would be there's weak or no correlation between the values being compared, if we could see that the regression value is towards 0 or -1. So since our regression value is 0.99149, we could see that this is nearing towards +1. Therefore, we could conclude that there is a strong correlation between the two methods of measurement, and that the developed system can replace conventional method of measuring pupillary distances, ultimately achieving the objectives set in this study. As for my recommendation, I could only recommend 3 different components to be applied. One, which is a better camera to better capture images of the subject, or rather their eyes. 2 is a better processor in order to speed up the image processing of the prototype. And lastly would be the implementation of a real-time video analysis, which would shorten the whole period of determining the subject's pupillary distance. So that being said, thank you so much for listening to my presentation, and have a great day.